In this video, we're going to introduce chapter 10, where we're going to talk about the rotation of a rigid object about a fixed axis. So the very first quantity that we're going to look at is called the angular position. And basically what the angular position tells me, it simply tells me the displacement of a point from some reference line. So as this disk is rotating in the counterclockwise direction, you can see that this point is moving from this point to this point right here. So again, I can calculate the change in the angular displacement theta if I know what the radius is and if I know what the arc length is s. So there is a simple equation that we can use. So theta is equal to s over r, where r is the radius and s is just the arc length. So notice that if I substitute theta equals to 2 pi, so by the time that we do 360 degrees, we know 360 degrees is equal to 2 pi, then I can calculate my circumference. So my circumference is just given by 2 pi times radius, which is the total arc length in one revolution. So again, we know that there is a relationship between the angle in radians and the degree. So the conversion is 1 radian is equal to 57.3 degrees. And again, so we can rewrite this equation. So the arc length is given by the radius times the angle, and we know that there is a relationship on how to convert my angle. So theta in radians is equals to pi over 180 times theta in degrees. Notice that for me to use this equation right here, I must convert my theta first into radians before I can use this equation to calculate the arc length. So that is something that you want to keep in mind. All right. So now let's talk about the angular speed. So basically, if you look at this axis right here, this is my x-axis and this is my y-axis. Now suppose that a point, so this point is rotating from point A to point B, and let's say that at point A the time is t initial, and at point B the time is t final. At point A the angle is theta initial, and at point B the angle is theta final. Then I can define my change in angle is theta final minus theta initial. Then I can also use that to calculate the average angular velocity. So this quantity right here is called the angular speed. So the average value of the angular speed is just the change in the angle divided by the change in time. Now we can also define the instantaneous angular speed. So the instantaneous angular speed, we calculate it by taking derivative. So it's just the derivative of the angle with respect to time. So again, these are two quantities that are very useful. So we have the average value of the angular speed, which is just delta theta over delta t, and you have the instantaneous value of the angular speed is the derivative of the angle with respect to time. All right, so this is quick quiz number 10.1, part 1. Again, I'll let you guys take a look at this quiz just to make sure that you can apply some of the concepts that we've already spoken about. So now let's move on to talk about the average and the instantaneous angular acceleration. So I can define my average value of the angular acceleration. So the angular acceleration is represented by the symbol here is alpha. So the average value of the angular acceleration is just the change in the angular speed over the change in time. So I can write it as omega final minus omega initial divided by t final minus t initial. So again, the symbol for angular speed, for angular acceleration, is alpha, and omega is the symbol for angular speed. Now, just as we can define the average value of the angular acceleration, we can also define the instantaneous value of the angular acceleration. And the instantaneous value of the angular acceleration, we calculated using this equation. So it's just the derivative of the angular speed with respect to time. All right, so something that we should remember here, so the difference between rotational motion and linear motion is that in rotational motion here, the displacement is theta. Meanwhile, in linear motion, the displacement is x. In rotational motion, the angular speed is omega. In linear motion, the angular speed is v. In rotational motion, the angular acceleration is alpha. In linear motion, the acceleration is just a. So again, this is how we can use this to compare angular quantities with linear quantities. All right, so let's talk a little bit about the directions of angular vectors. So if you look at these two pictures right here, you can see that in the first picture, the rotation is in the counterclockwise direction. Meanwhile, in the second picture, the rotation is in the clockwise direction. So generally, we say that counterclockwise is considered positive. So whenever you have a counterclockwise rotation, it means that this is a positive rotation. And when you have a clockwise rotation, this is a negative rotation. So again, we can say that the angular speed is a vector quantity, the angular velocity. So if this is counterclockwise again, it means that this is a positive value of the vector, is pointing up. And if this is clockwise, it's pointing in the opposite direction. So this will be considered negative. All right. So now we're going to do some analysis right here. So we're going to look at a rigid object that is under constant angular acceleration. So again, just as we did for linear motion, if you remember those motion equations that we derived in chapters 2 and 3. So if alpha is a constant, so if alpha is not changing, then I can say that I can rewrite this equation as d omega is equals to alpha dt. And then if you just do this integral right here, because alpha is constant, you can obtain this equation. So omega final is just equals to omega initial plus alpha times t. So whenever alpha is equals to constant, I can use this equation to calculate the final value for the angular speed just by, it's just equals to the initial value plus alpha times t. Now if I know omega, I can use that to find my angular displacement. So again, if you just integrate this equation right here, you end up with this final value here. So theta final is equals to theta initial plus omega times t plus 1/2 times alpha times t squared. All right. So now we can put all of these equations together. So sometimes we can combine these two equations. So by combining these two equations here and doing a little bit of algebra here, we can derive this third equation. So omega final square is equals to omega initial square plus 2 alpha times theta final minus theta initial. So again, this equation is going to work when alpha is equals to constant. All right. So sometimes also we can define this. We can rearrange this equation to define theta final using the average value. So sometimes we can approximate the acceleration, the angular acceleration, just by taking 1/2 times omega initial plus omega final. So all of this is my alpha. So this would be a good approximation for my alpha value. So again, this is an equation that I can use to calculate my theta final. All right. So this picture that you see, this table shows me the relationship between the rotational and the translational. So the translational means that This is motion in the x, just in the x direction. Meanwhile, the rotation means that I'm looking at changes in angle, angular velocity, angular acceleration, and angular displacement. So generally, you can see that if you have a particle under a constant acceleration, then the v final is just equals to v initial plus a times t. X final is equals to x initial plus v initial t plus 1/2 at square, and v final square is equals to v initial square plus 2a into x final minus x initial. So those are equations that I can use to solve the motion of a particle under a constant acceleration. Now we can do pretty much the same if you have a particle that is under a constant angular acceleration. So if the angular acceleration is constant, then I can say that omega final is equals to omega initial plus alpha times t, theta final is equals to theta initial plus omega initial t plus 1/2 alpha times t square, and omega final square is equals to omega initial square plus 2 alpha into theta final minus theta initial. So we're going to be using these equations here to solve problems, just as we use these equations as well here to solve problems for translational motion. All right. So now we're going to look at one example here. So again, whenever we're trying to solve a problem, so if the problem tells us that the alpha is constant, so you have an object that is rotating at a constant rate, so alpha is not changing, so alpha is equals to constant. So whenever I know that alpha is equals to constant, it means that I can apply these equations here to analyze the problem. So I could use any of these equations here to analyze the problem. So now let's look at one example here. So let's suppose that, so this is example number 10.1, and this is the example of a rotating wheel. So suppose that a wheel rotates with a constant angular acceleration of 3.50 radians per second square. And then it says that if the angular speed of the wheel is 2.00 radians per second at t equals to 0, through what angular displacement does the wheel rotate in 2.0 seconds? So in this problem here, so what we're going to do is that I want to calculate this angular displacement, and it tells us what the angular acceleration is. It's a constant value. It tells us what the initial angular speed is, and I want to calculate the angular displacement at t equals to 2.0 seconds. So if I go in and use this equation here, so my change in theta is equals to theta final minus theta initial, which I can write this as omega I times t plus 1/2 times alpha times t squared. So again, if I plug in my values, my omega I is equals to 2.00, my t is 2.00 seconds, my alpha is 3.5. So if you plug in everything into this equation here, you get 11.0 radians. And 11.0 radians, you can write it as 630 degrees. All right. So we know that, so because one revolution is equal to 360 degrees, if we just divide 630 by 360, it means that you get a total of 1.75 revolutions. And then if you want to calculate the angular speed of the wheel at t equals to 2.00 seconds, then we can just go in here and we use this equation. So omega final is equals to omega initial plus alpha times t. If you plug in the values for omega initial and alpha and t, you get 9.00 radians per second. So we're seeing that the angular velocity, the angular speed has increased from 2.00 to 9.00 radians per second, and this is because there is an acceleration in the system. Now let's look at this example here. So it says that suppose a particle moves in a straight line with a constant acceleration of 3.50 meters per second. If the velocity of the particle is 2.00 meters per second at t equals to 0, through what displacement does the particle move in 2.0 seconds, and what is the velocity of the particle at t equals to 2.00? So this is the problem that we've solved already in chapters 2 and 3. If you plug in the values here, you calculate your delta x and your VI as 11.0 and 9.00 meters per second.